when greater magnification is required to view microscopically smaller objects, a compound microscope is used. A compound microscope consists of two convex lenses arranged coaxially. The lens O, that is close to the object to be viewed, is called the objective, and the lens E, that is close to the eye, is called the eyepiece. The objective of a compound microscope is of a small focal length and has a small aperture, whereas the aperture of its eyepiece is large. Let a small object AB be placed at a distance that is just greater than the focal length of the objective FO. When the light rays from the object are incident on the objective forms an image A'(B'), which is real, inverted, and magnified. This image A'(B') acts as the object for the eyepiece. If the position of the eyepiece E is so adjusted that A'(B') lies between the optical center and the first principal focus, then a virtual and magnified final image A'(B') is formed. Let the height of the object AB be h and the height of the image A'(B') formed by the objective be h'. Let us also define the tube length L of a compound microscope as the distance between the second focal point of the objective and the first focal point of the eyepiece. If MO is the magnification due to the objective and theta is the angle that the ray refracted by the objective makes with the principal axis, then MO is equal to h' by h and tan theta is equal to h by FO, which is also equal to h' by L. From these two equations, we get MO is equal to L by FO. Let this be equation 7. If the eyepiece is adjusted in such a way that the image A'(B') is formed between the first focus FE and the optic center of the eyepiece, and it is very close to FE, then the final image is formed at far point. Then we say that the compound microscope is set in normal adjustment. Since the eyepiece acts as a simple microscope, using equation 3, we can write the magnification due to eyepiece ME is equal to D by FE. Let this be equation 8. Since the image formed by the first lens becomes the object for the second lens, the total magnification of the combination M is the product of the magnification due to the objective and the magnification due to the eyepiece. Therefore, M is equal to MO into ME. Substituting the values of MO and ME from equations 7 and 8, we get M is equal to L by FO into D by FE. That means, when set for normal adjustment, the magnifying power of a compound microscope M is equal to L by FO into D by FE. If the eyepiece is adjusted such that the final image is formed at the near point, then, using equation 6, ME is equal to 1 plus D by FE. In such a case, the magnifying power of the compound microscope M is equal to L by FO into 1 plus D by FE. For larger magnification, the objective and the eyepiece of a compound microscope must have small focal lengths. The magnifying power is generally expressed in terms of x, where x is the number of times the size of the image appears to be when compared to the size of the object. For example, if a compound microscope is marked as 10x, then its magnification is 10, and It denotes the number of times the size of the image appears to be when compared to the size of the object. In fact, the objective and the eyepiece of a compound microscope are made of a multiple lens system. This improves the quality of the image and minimizes various optical defects. The telescope is an optical instrument that is used to view distant objects clearly. The astronomical telescope is used to view celestial bodies, and the terrestrial telescope is used to view distant objects on the Earth's surface. Let us now study about an astronomical telescope. Consisting of two converging lenses placed coaxially. One of the converging lenses is called the objective, which is closer to the object to be viewed, and the other is closer to the eye and is called the eyepiece. To capture the image of a distant object, the objective must gather large amounts of light, and hence the aperture and the focal length FO of the object is large. The eyepiece of a telescope has a small aperture and a small focal length FE. When the telescope is turned towards a celestial object, parallel rays from the distant object are incident on the objective, which form an image AB at the focus FO of the objective, and this image is real, inverted, and of point size. The image AB acts as an object for the eyepiece, and the final image A-B- of the distant object is formed by the eyepiece. The image A-B- is virtual, magnified, and is inverted with respect to the original object. Let the angle subtended by the object at the objective be alpha. Since the object is far away, the angle subtended by it at the objective is same as the angle subtended by it at the eye. Let beta be the angle subtended by the final image at the eye. The angular magnification, or the magnifying power of a telescope M, is the ratio of the angle subtended by the final image at the eye to the angle subtended by the object at the unaided eye. That means M is equal to beta by alpha. Let this be equation 1. Let us now derive an expression for the magnification of an astronomical telescope when it is set for normal adjustment. The telescope is said to be set for normal adjustment if the final image is formed at infinity. If the image AB is on the focal plane of the eyepiece, then the final image is formed at infinity. Since the two angles alpha and beta are very small, tan alpha is approximately equal to alpha, and tan beta is approximately equal to beta. But tan alpha is equal to AB by FO, and tan beta is equal to AB by FE. Hence, for small angles of alpha and beta, we can write that alpha is equal to AB by FO and beta is equal to AB by FE. Substituting the values of alpha and beta in equation 1 and on further simplification, we get M is equal to FO by FE. Let this be equation 2. Hence, we observe that the angular magnification or magnifying power of a telescope that is set for normal adjustment is the ratio of the focal length of the objective to the focal length of the eyepiece. In this case, the length of the telescope tube is equal to FO plus FE. It is important to note that the final image formed by an astronomical telescope is inverted. There is no difficulty for the viewer as most of the celestial objects are spherical in shape. If the astronomical telescope is used to view a terrestrial object, then the final image being inverted would be a cause of discomfort for the viewer. To overcome this problem, we use a terrestrial telescope which produces a final image that is erect with respect to the object. Electric dipole comprises of a positive charge and a negative charge separated by a finite distance.
Electric flux. The electric flux through a surface held inside an electric field represents the total number of electric lines of force crossing the surface in a direction normal to the surface.